right, I apologize for running a little behind, but jump in, and if anybody has any questions, feel free to ask them now. My notes app is not working. Come on. I don't know what's going on with this thing. It's all right. More than one way to skin a cat. Let me grab it. Grab the handout again. We'll just work from that. I'll transfer everything over. Oh, stop backing up. I ain't asking you to do it. One second. Technology sucks when it doesn't work. It's awesome when it does, but when it doesn't, not so much. Let me share my screen and then we'll get started. So we're going to start working through these substitution and elimination examples. So let's do that now. I think we did E2 and E1 on Monday. So let me share my screen and then we'll start it. All right. We've talked about the substitution, elimination. I think we left off here saying that it was SN2. Let's finish this and then we're going to work through some more examples. Yeah. All right. So if you look right here, we said that this was SN2. So we looked at the next question based on your answer to question 1. What is the correct rate law for the reaction shown above? What would you choose? If you know the mechanism is SN2, what does the 2 stand for in that description?
Bimolecular.
Bimolecular. What does that mean in terms of the rate?
It would be K times the substrate times the nucleophile.
Yes, that's exactly. So we could look at the answers here and see that this answer matches that. ROAC is just the R is abbreviation for the rest of the nucleophile, and the OAC is my leaving group. Right. So if we look at sorry, wrong one. If we look at here. Okay, so that's my substrate. Somebody need to close that door or take the key out. That's my substrate, and then that's my nucleophile. All right. So if we know it's SN2, we know it's got a 2-term rate law, it's bimolecular, and both the nucleophile and the substrate are involved in the rate determining step. So the correct rate law would be the substrate, ROAC, which is, again, the R is just an abbreviation for that chain that's connected to the leaving group, and then the sodium methyl sulfide, which is my nucleophile, right? So that's right here. All right. And the next question, let's answer that, and we're going to jump down to another page. If the concentration of sodium methyl sulfide is decreased by 10 times, what happens to the rate? If it's SN2 and it's following that rate law, what happens if I decrease the concentration of sodium methyl sulfide by 10?
%. I mean, 10 times decrease.
It should decrease, the rate should reduce by 10 times, right? So if I show the rate law as,
This is mine.
right, if I show the rate law as K times, let's say for the substrate, I put 1, and for the nucleophile, I put 1/10, right? Because that's a 10 times decrease. Then the rate is going to decrease by 10. Because, again, the rate for SN2 is dependent on both the nucleophile and the substrate. All right, we look at this next reaction. It says the reaction of R2-methyl-3-bromobutylbenzene with sodium methoxide gives 2 products. Choose the best representation of the transition state of the reaction listed below. What type of reaction is this? What type of reaction is it? Is it a substitution or is it an elimination?
Substitution.
It is a substitution. Which mechanism is it going to follow? And to understand that, we need to look at all the factors. We need to look at the solvent, the substrate, the products, all that, all of those are clues to the mechanism. What do you notice in the products that gives this away? That gives the mechanism away?
Would it be the inversion of stereochemistry?
Well, it's inversion on one of the products, but you actually get 2. If it was only this one, and that's a great answer. If it was only that product, then we could say it was inverted, but actually this gets racemized, right? You get both products. So you see some racemization.
So then that's the giveaway.
That's the giveaway. So what mechanism would they follow?
SN1.
It's SN1, good. Right, because it gets racemized. I mean, and the reason that racemization can happen is because you go through this carbocation intermediate that can get attacked. In this case, the carbocation intermediate would look like this, right? Where I have this, not that. Come on, Russell. Right, that carbocation is actually an empty p orbital. So when my nucleophile comes in, I can't draw a plus sign, I'm about to retire. All right, when that nucleophile comes in, what's the nucleophile? Ethoxide. Right, it can attack from here or here. Right, either side of that load can get attacked, right? And so because of that, you're going to get a racemic product. You're going to get racemic products where both stereoisomers are formed, right? So it's SN1. So what would be the transition state for the first step? Because what is the first step if it's SN1?
Loss of leaving group.
Good. So the loss of leaving group is the first step. The second step is nucleophilic attack. All right. So if the loss of leaving group is the rate determining step, and the first step, that's the step that we're concerned about in that second part of that question. Which one of those transition states can we rule out? Remember, this is SN1, it's unimolecular, which means that the nucleophile is not involved in the rate determining step. So which transition states can we rule out?
1 and 2.
1 and 2, right? Because both of those involve the nucleophile. So we get rid of, we don't need that. All right, now between 3 and 4, which one of those is accurate, right? If the first step is the loss of the leaving group, which happens like this, right? Where the electrons in that bond leave with bromine, right? Which transition state between 3 and 4 is going to be the correct one? Remember, in the transition state, you got partially broken bonds and partially formed bonds. So the loss of the leaving group, as you go from starting materials up to the transition state, you're breaking the carbon-bromine bond. That's the only thing that's happening.
Is it the third one? Oh.
This one?
Yeah.
Yeah. Why do you say that?
Because when the leaving group leaves, I feel like it would be partially positive, and then the bromine would be partially negative. Like it's gonna take.
Bromine is leaving with a pair of electrons. So you're right. The charge on it is going to be partially negative in the transition state until it comes all the way off and becomes fully negative. And then the carbon, where the carbocation is going to be becoming positive. So it's partially positive until bromine fully leaves, right? This is not correct because bromine is not going to have a partial positive charge.
I have a question.
Go ahead.
So back to when you were talking about the racemization, were you saying that that was kind of like the giveaway?
Yes.
Because with the SN2, it's supposed to come from like the opposite side, and this time it comes from either side.
Yes. So for SN2, you get inversion because the nucleophile is coming in at the same time that the leaving group is leaving. SN1, you get racemization because the leaving group leaves first and you're left with a carbocation intermediate. That can get attacked by your nucleophile from either side, which I had shown down here. All right. Did that answer your question?
Yes, it did. Thank you.
Okay. So it's transition state 3 because the charges match up, and the only thing involved in that transition state for the rate determining step is the loss of the leaving group. So that dashed line means that that bond is breaking. All right. Let's go on to another problem. Let's look at 861. We're going to look at 861. D, and we've already did one like B. Let's do A and D, and then over here we're going to do A, C, and Let's do that. And then we'll come back and we'll do 742 and 743. We got time. And we'll do 744 and 741. And then I'm gonna leave you to do this one on your own. All right. So now let's go up to, let me cut this out so we can have room to work these things. Because I want to show the arrows on one of them. All right. So we have in A, we have a alkyl halide substrate. We have a strong base, sodium hydroxide, right? And it says predict, it's giving you right here, it's telling you, predict the major product for each of the following E2 reactions, right? So let's take A, I'm gonna cut that out. We're gonna go through the mechanism. It's telling you that it's E2 off the break. So it's not, you don't have to wonder about the mechanism. So if this is A, what am I looking for if I know that this is an E2 elimination?
A strong base.
Okay, so we have that, right? We got sodium hydroxide, good. So I'm just gonna write out the OH here. That's negative. You know, anytime you see sodium again or potassium, as in D, that is a counter ion. So it's a counter ion for a negatively charged atom or functional group. All right. So now I have my base. What else do I need to locate?
The leaving group.
Leaving group, good, which is here, bromine. So I got my leaving group. Now what do I need to locate? So I have my base. I know what my leaving group is. Where is the elimination going to take place?
The alpha proton.
Alpha protons. Who was that?
Carlin.
Good, good. Thank you. That's excellent. And the alpha protons are on the carbons next door to the leaving group. So I'm gonna put protons in here. I'm gonna change the colors on them. Do some different colors. I'll do this since that's the color I'm wearing today. That's that. And then we'll put another set of protons over here. Remember, you're going to get two products because you got two sets of alpha protons. Which one do you want to do first? Let me move this. Which side? Did you say the pink side?
Yes.
All right. All right, so let's put the arrows in for that. So this is coming here, boom, like that. I'm gonna break that CH bond and put that, notice where my arrow went, between the carbon where the protons are and the carbon where the leaving group is, right? And then I wanna break the carbon bromine bond. All right, so that's gonna give me one of my products, which is gonna be that. Make sure I got enough carbon. Oh, hold up, I need another carbon. That's one product, right? Plus, let me draw the side products, water. All right, so the OH picked up a proton, so that becomes water. And then plus, sodium finds now whatever's negative, so that's positive. And then bromine is negative. All right, that's one product. Where's the other product going to come from?
Attacking the other alpha.
It's just going to attack the other side. Isn't it? Trying to cheat, but it ain't working out. So I'll just redraw it. So the OH now is going to come here, another molecule of OH. Boom, here. Let me change the colors on the arrows since we're not actually redrawing the substrate. So that's coming there. This pair of electrons is coming here. And then this pair of electrons is coming here like that. It's all concerted. It's all happening at the same time. So then that product is going to, and then you'll get the same side products. You'll get a water molecule, sodium bromide, salt, and then you'll get your product, which in this case, the double bond is going to be here, like that. Yep. So you get both. But the question asks for which one is major. Now, how do we predict which is major and minor? What's the rule?
Does that see the
Yeah, come on with it. I don't care if you say it wrong, just say it.
Does that Zep? Yep, that's the one.
Zep's rule. Good. What does that rule say about eliminations? Which product is going to predominate?
The most substituted.
Yep, the most substituted alkene, which will happen to be the most what? Stable. Right, so basically it's under thermodynamic control. So you get the more stable product as the predominant product. Good. All right, let's do D. We're not gonna go through the mechanism because we should be familiar with the arrows now, but I'm gonna cut it out so we can write the products. And the reason I'm doing D is because there's a different type of base there. Right, that base, I showed you that the other day, is sometimes you'll see it written like this. K-O-T-bu, right? Tert-butyl. It's potassium tert-butoxide. It's a very, very strong base. The tert-butyl group is really electron rich. And so it makes those electrons on oxygen very, very basic. Right, so it's that, and then K plus, like that. Very basic, very strong base. You use that when you have protons that have a little bit higher pKa that you need to remove. Yeah, so let's crop this out right quick. Let me move this too. All right, so without going through the actual arrow pushing, we got our base. What are we looking for now? We know it's E2. So what's the strategy?
The leaving group.
Find a leaving group and then find the alpha.
The alpha proton.
Alpha protons are going to be here on this carbon and here on this carbon. So we can predict the products, right? Without going through the mechanism. Where's the double bond going to be if I pulled off this proton? Where would the double bond end up?
To the right of the bromine.
Right here. Let me change colors. Right there.
Yes, sir.
Mm-hmm. And where would it be if I pulled off these protons? The protons on the other side. Where would they, if I pulled off one of these protons? Where would it be?
To the left of the bromine.
It'd be right here, right? Even if you don't know the mechanism, if you implement this strategy where you find the leaving group and find the alpha protons, you can draw the products even if you don't know how to push the arrows, because the elimination is always going to happen between the carbon where the leaving group is and the carbon that's adjacent to it every single time. right? So let's draw. Well, I wish I could cheat, but I'm not gonna cheat. I'll just draw it. Let's draw the first product. Oh, hold up. I don't think we said which one of these was major. Right up top, we didn't complete that. The second product is major. Why?
Because it's the most stable, or like most substituted.
Yeah, it's a disubstituted alkene, right? You can see that the double bond is here, and then what's not hooked. I hate that word for chemistry. What's attached to it are these two carbons right here, so it's disubstituted. Up top, the double bond is here, and it only has one carbon bonded to it. But everything else is hydrogen, so it's monosubstituted. All right. So now let's go down here and draw a product. So we're going to put in, this is all. So this is one of my products. And then this is the other product. Am I right? Fix this isopropyl group. Yes, no?
Yes.
Mm-hmm.
Yes.
Which one is major?
The second one?
Second, this one?
Yes.
Yeah. You can see that it's tri-substituted. You got a group here, and a group here. And those groups are attached to your alkene. Right, same here, boom. You only have one group attached right here. So it's monosubstituted. So this is going to be a much more stable alkene than the top one. So this will be tri-substituted. I'll write that in. All right. Any questions about those two examples? All right, let's go up here and let's look at 741. We got plenty of time. For each pair of the following compounds, identify. It says identify which compound will react more rapidly. So that's the question right there. Which compound will react more rapidly in an SN1 reaction? So there's your clue. It's SN1. What are we looking for in SN1? We're looking at the structure of the substrate, preferably tertiary or allylic or something that can stabilize a carbocation, because you know it's going to go through a carbocation intermediate. And then we're looking at the leaving group. So we're looking at, for this particular problem, substrate structure, and that's just if it's primary, secondary. Come on, Russell. Or tertiary, right? And leaving group. How do we determine leaving group quality again? Anybody remember that? What are we looking for?
The pKa.
The pKa of the conjugate acid. All right. So if we look at A, what are we comparing in A? Look at the carbon where your leaving group is. So here we're comparing substrate structure, right? This is a tertiary carbon. And this is, what type of carbon is that? It's primary. Mm-hmm. So what does that mean in terms of the rate of the reaction? Which one of those is going to form that carbocation faster? Because remember,
Tertiary.
the tertiary. Remember the rate, not the rate, but the trend for carbocation stability, right? Is the tertiary is the most stable carbocation, and then secondary, and then primary, and then methyl. Methyl is the worst. Tertiary is the best. Did we talk about this already? Did we talk about hyperconjugation? Was that in this class or was that in my part one? I can't remember. It's running together now.
Yes.
We did talk about it. Okay. All right, great. So this is going to be faster. All right, let's look at the next one. At B, what do you think? Look where your leaving group is. Look at the structure, the bond order on that carbon. Tell me which one of those is going to more readily form a carbocation. Because that's what this question is really asking.
The second
one.
Second one. That's a tertiary carbon. So that's going to be faster than this one, which is again, a primary carbon. All right, let's go down here to C. What do you think? Both of those carbons are secondary. What are we looking for now? Notice this one is allylic because that leaving group is on a carbon that's adjacent to a double bond. This one isn't. What can that allylic system do if I put a plus charge where that chlorine is? Take the chlorine off and make that carbon positive.
Resonance.
Resonance, which offers what? Stability, right? So if I can do resonance, so this is what we were comparing in that case. Dude, keep calling me, bro. I'm in class. We're comparing here versus here, right? So that carbocation, that allylic carbocation can be stabilized by resonance. So what that means is that carbocation is going to form faster because when it forms, there's some stabilizing factor that's going to stabilize it after the fact, right? So it's that's going to be stabilized by resonance, right? What about D? What are we comparing there? Because both of those are tertiary carbons.
Is it the size?
Not in this case, right? Okay. Look at the difference. What's the difference in the two molecules?
They have different leaving groups.
Different leaving groups. And so now what we're looking at in that case is which leaving group is going to leave more readily. How do we determine that?
pK of the conjugate acid.
Yep. So look at your list. If you have your handout in front of you. Tell me what the pKa is for HCl. Anybody? Is it like -9, something like that?
I don't see HCl.
You don't see a chlorine?
I see. Oh yeah, I see chlorine. Yeah, it's -7.
-7. All right, and then the tosylate we said, which was here, right, is -0.6. So which one of those has a lower pKa?
OTS.
OTS is moving closer to 0. Remember, those are negative numbers.
Oh.
So -7 is smaller than -0.6. So the HCl has a lower pKa. The conjugate acid of chlorine or the chloride anion has a lower pKa than the tosylate anion. All right, so that means that the HCl or the chlorine is going to be a better leaving group. So that means this reaction is going to be faster, right? Because if either one of them leave, you're going to get a tertiary carbocation. But the fact that the chlorine is a better leaving group, that reaction is going to be faster than the substrate where the tosylate is the leaving group. Does that make sense?
Yes.
All right.
Yes.
We're going to do 742 right quick and 743 because we only got 5 minutes. And then on Friday, we're going to do a few more problems, and then we'll probably start another section because I think we've been talking about this we started talking about this last Friday on the day of the exam. Is that right?
Yes.
All right. So we're on schedule. We're good. Let's do 742 and 743 and 744 real quick. It's not going to take that long. I said, consider the following reaction. Look at the reaction. Somebody tell me what type of reaction that is and what the mechanism is. Not the arrows, the type of mechanism. Because up to this point, we've studied SN2, SN1, E2, and E1, right? So what type of reaction is it? Is it a substitution? Is it an elimination? And then if it's either one of those, what type of mechanism is it? E2, E1, SN2, SN1. Help me out. I'm tired now. I'm getting old.
SN2.
SN2. I 100% agree with that. Now, how did you come to that conclusion?
The inversion of stereochemistry, and it's only one product.
You got inversion. That's good. You got an aprotic solvent. You have a secondary substrate. All those things point to, well, really the solvent and the inversion both point to SN2 because secondary substrates can do SN1 or SN2. Very good. All right, so now that we know it's SN2, let's answer the questions. How would the rate be affected? So this is a rate question. So you need to know the rate law for SN2 in order to answer that. All right, so rate is what? K times the concentration of what?
The substrate and the nucleophile.
Yes. Good. Let me move that over. Shrink it down. All right. So how would the rate be affected if the concentration of the alkyl halide is double? So the alkyl halide is my substrate. That's this one, right?
It'll double.
The rate should double. Excellent. All right, how would the rate be affected if the concentration of sodium cyanide is double? That's your nucleophile, sodium cyanide.
The reaction will also double.
Yeah.
Or the rate, sorry.
Yeah, the rate is going to double with that too. Because for SN2, the rate is dependent on both the nucleophile as well as the substrate. All right, let's look at 743. What do you think? What type of reaction is it? What mechanism did it go through?
SN1.
Okay, great. I agree. It's a SN1. So again, the first question is about the rate. What's the rate law for SN1?
R equals the concentration of the substrate.
K times concentration of the substrate. Good. So now let's answer the question. How would the rate be affected if the concentration of the alcohol, which is your substrate, is doubled?
The rate would double.
Rate would also double. This is my substrate. That's my alcohol. And the rate will double if you double the concentration of the substrate. Good, excellent. What about B? What about double the concentration of HBr?
No.
It would stay the same.
The rate would not change. Very good. Right, no change in the rate in that case, because HBr is not involved in the rate determining step. If it were, this wouldn't be unimolecular, it would be bimolecular, right? So the fact that HBr doesn't affect the rate, that means that I can triple it, quadruple it, I can quintuple it, it doesn't matter, it will not change the outcome, because the rate determining step happens when the OH is converted into a leaving group and it leaves spontaneously, right? That's the only thing that affects the rate is the loss of the leaving group. Good, I think it's clicking. This is good. All right, let's look at 744 and then we're gonna stop. It says classify each of the following as protic, each of the following solvents as protic or aprotic. So what is, let's do water and ethanol. What do you think? Ethanol is an alcohol. Water is water. It could be well, let me not say that. What do you think? Protic or aprotic?
Water is protic.
What about ethanol? All alcohols are protic. All right, all alcohols are protic. Alcohols, acids, water, carboxylic acids, all protic. They can all give up H+. Okay, so with DMF, I gave you a list of these, by the way. DMF, DMSO, and ammonia. Those are all aprotic. So I can write this in. This is what DMF looks like. Dimethylformamide. DMSO is dimethyl sulfoxide. Looks like this. That's not protic. And then of course, ammonia is just NH3. And then it might be tempting to think that those protons on ammonia are acidic, but they're not. The pKa of ammonia protons is somewhere around 40, 35 or 40, something in there. It's actually on that list too. So those are all aprotic. Let me find that list right quick again. I think ammonia is on there. Yeah, it's 36. Because this is NH2. The conjugate acid of that would be NH3. So pK is 36. That ain't going nowhere. It's not being donated. All right, we got to stop here. I went a little bit over. I apologize. I also apologize for starting a little bit late. But I had to submit some paperwork before class started. So with that being said, we'll stop here. We'll pick up on Friday, finish out this handout, and then we'll start a new topic on Monday. We're going to start conjugated dienes. And before we go, did I send out already the ranking nucleophiles videos? I think I did. Like how to rank them in terms of their nucleophilicity.
I don't think so, but I can double check. I don't think so.
I'm almost certain I sent it Saturday. Because remember, I couldn't post the notes on Friday. I had something I had to do, but I posted the video, the recording, and the notes on Saturday. I think I sent it out Saturday. But I'll double check. If I did not, then that's what I'm going to send, because that's what we're going to be doing on Friday, ranking nucleophiles. All right, everybody good?
Yes, thank you.
Yes, sir.
All right, y'all have a great rest of your day, and I'll see you on Friday.
Thank you.
Thank
Have a
you.
good day.